Welcome back, folks. Last thing to look at here in section 6.2 is an enzyme kinetics, so it's going to get a little bit mathy again. Okay, before we get into that, it's probably important to think about why it's important to think about the rates at which enzymes are working. By understanding how quickly enzymes are doing their jobs, we learn a lot about certain cellular processes, and that's because many, not most, cellular processes at some level are under the control of enzymes. And so if we think about, for example, a cell responding to a signal in its environment, for example, the signal transduction or signal reception process, the signal transduction process, in some cases the response is governed by enzymes. And so by looking at how rates of enzyme turnover in terms of catalytic activity change in response to certain conditions, we learn about the cell's behavior and how quickly a response may or may not occur. So there are lots of examples like that. So let's start taking a quick look at some enzyme kinetics. So this describes, enzyme kinetics generally describes the quantitative aspect of enzyme catalysis. So it's kind of like a way to put numbers on how quickly or how slowly an enzyme is doing its job, and that's to convert substrates to products. So reaction rates, how quickly a reaction's occurring, are affected by the concentrations of the substrates, the concentration of the products, and things like enzymatic inhibitors, which we won't get into, but I'd encourage you to think and read about enzyme inhibitors. So if we start off thinking about an initial reaction rate, those are measured over brief periods of time during which the substrate concentration hasn't decreased to the point that it would affect the rate of the reaction. So the initial reaction velocity, measured as V, is the rate of change in product as a concentration per unit time. And that primarily, to start with for us, it's going to depend on the substrate concentration. So if we're down here in this part of the graph, at low concentration substrates, so down here on this, before we get into the slopes and stuff, down here on this axis here we've got substrate concentration, and up here we've got velocity. If we're down here in this part of the curve, just down here, we can see that initially down here at pretty low substrate concentrations, when we have a doubling of S, we'll get a doubling or a proportional change in the velocity of the reaction. But as we see the substrate concentration increasing, we start to see a slowdown in the increase of the velocity of the reaction. And if we plotted this line out, effectively what I guess is to infinity, we would hit a point where the reaction cannot go any faster, and that point is called Vmax. And so Vmax is the maximum velocity that you can get from a given concentration of enzyme as we've increased the substrate concentration to the point where the enzyme can't act on the substrate any quicker, so it can't do its job any faster than it's doing it. So it doesn't matter how much you give to how much substrate you give to the enzyme, it can't go any faster. So it's kind of like if you gave me I don't know, what should I say, 3 ice cream cookie bars, for example. I can eat them all. Let's say I can eat them all in a minute. And then you give me 4, and I can get that done in a minute as well, and I can eat all those. And you give me 5, and I kind of get through a little bit of that. If you give me 6, or you give me 7, you give me 8, I can't do any more than about 4. And so you can keep giving me, cookie ice cream bars, but I can't eat them any quicker. And in your book there's a kind of a neat explanation of this in terms of monkeys shelling peanuts. And the monkeys eat peanuts? I don't know, give them bananas or something, I don't know. So once you hit this substrate concentration where the enzyme can't actually convert the substrate into the product any faster, because it's basically got hold of a substrate, it can't get hold of another one at the same time, you see this graph this slope here just kind of eventually it will completely drop off. It won't drop off, it will just plateau out, and that point is called Vmax. It's the maximum velocity. There's another interesting variable here, half the Vmax. So that's half as fast as the reaction can possibly go. So half the maximum velocity. We call that the Km. So the Km is the substrate concentration at half the maximum velocity, and you can gain some interesting information from Km, and we'll come back to that at the end. So I think that's all we need to talk about about this graph. So let's kind of move on to some quantifications of what's going on in the graph. Let's just start off with a kind of a general scenario. We have a substrate S, and it's converted to a product P by the enzyme E. That's just a general, generic way of explaining a reaction here. Let's break this down into more steps and think about what's happening in each step as we go. So in the middle here, we've got this looks pretty complicated and intimidating, but it makes sense if you think about what each of these variables means. So EF is the enzyme in a free form. That means it's not bound to substrate, and here's the substrate S. So to start with, we've got to have a collision between the enzyme in the unbound substrate form and the substrate. So that's what's being set up here. And so if the enzyme in the free form binds with a substrate, there's a certain rate at which that will happen, and that's going to be impacted by the enzyme concentration, the substrate concentration, and things like temperature. So that's given a constant K1. And so the enzyme substrate complex forms at a constant K1, and that's a function of the enzyme concentration, the substrate concentration, temperature. Now that process is reversible because the substrate can also be released before it's converted to product, and so that is a constant K2. So this is a dynamic state. Just because a substrate is bound to an enzyme doesn't mean that we're going to get catalysis. Now if we, on the other hand, do convert the enzyme substrate complex into the product, then we end up with a free enzyme in a free form plus the product, and that's under the influence of K3. And there are some enzymes we actually convert back again, and so that will give us the constant K4, where the product can bind and maybe form the substrate complex, the enzyme substrate complex. So that equation in the middle, that reaction in the middle there, just summarizes the relationship between the enzyme in the free form, the substrate, the enzyme substrate complex, and then the release of the product from the enzyme, which returns the enzyme to its free form. And so we've got these constants which help us think about the rate of enzyme substrate complex formation and then catalysis of the reaction or conversion of the substrate S into the product P. So K3 is probably the most important thing to think about here. So in a moment, what we'll do is we'll look at this relationship between velocity and Vmax and the substrate concentration and Km using 3 different examples. We'll come to that in a moment. There's something else I want to look at first. Before we get there though, the velocity of the reaction is described by this relationship here. The maximum velocity rate multiplied by the substrate concentration over half of Vmax, which is Km, plus the substrate concentration. So we're going to think about the influence of substrate concentration on velocity using 3 different scenarios in a moment. Before we do that, let's just look at Vmax in a little bit more detail. So don't forget, Vmax is the upper limit that's determined by the time it takes for the catalytic event to happen. That's me eating the ice cream cookie bars, or it's the monkey shelling the peanuts, peeling the bananas, or whatever. And that's independent of the amount of time it takes for the collision to occur between the substrate and the enzyme. And so Vmax can only be increased by increasing the enzyme concentration. Okay, so if we put more enzyme into a reaction, as long as there's plenty of substrate, then the reaction will go faster, because now we're adding, it's like duplicating me. If there's one of me, I can do 4 cookie bars, ice cream cookie bars at one time. If there are now 2 of me, I can do 8 at one time. As long as there are enough cookie bars, obviously I can do 8. And if we had 3 of me, as long as I get enough cookie bars, I can do 12. And so it would be 12 per unit time, rather than me on my own would be doing 4 cookie bars. And the monkey peanut example in the book kind of explains that a little bit more fully. So the slope of the line here is really given by this constant K3, which is the rate at which the substrate is converted to the product. And so that's what limits the slope of this. So Vmax will increase quicker, so the line will get steeper here if the enzyme can turn substrate to product faster, and that rate varies. Some enzymes, they kind of dawdle along. It's like walking behind that person who's texting on their phone. It doesn't happen very quickly. Crossing the street takes longer if you're behind that person texting on their phone. But if you're walking behind me crossing the street, we're across there pretty quickly. So different enzymes have different turnover rates. That's called kcat, and we'll come back to that in a moment. That's a catalytic constant, and we'll come back to that in a moment. It's the frequency or the rate at which the substrate is converted to the product. So that's the relationship between Vmax. We can increase Vmax, remember that's the maximum velocity, by adding more enzymes. So as enzyme concentration goes up, Vmax goes up as a function of how quickly you can convert substrate to product for a given enzyme. That varies. So let's look at these 3 different scenarios to kind of start to get a bit of a better handle on reaction velocity. So if we look at the situation where the substrate concentration is much, much less than the substrate concentration at half Vmax. So remember Km, that's the substrate concentration that you're at half Vmax. So Vmax, and then if we take half of that value, the substrate concentration which gives us Vmax, gives us half Vmax, that's the Km, or the substrate concentration at half Vmax is the Km. Then because the substrate concentration is so low, relative to the Km, it doesn't really have any impact on anything. So if we take this equation here, which is the one we started with in a moment, this variable here doesn't really it's so small relative to the Km. It doesn't really have any influence. So at very low substrate concentrations compared to the Km, is what we find is the velocity reaction is kind of roughly proportional to the substrate concentration. So that gives us a bit of an intuitive feel for what's going on here. Let's take the extreme opposite example of that. The substrate concentration is much, much greater than the Km. These 2 arrows mean greater than, and if they're the other way around, they mean less than. So the substrate concentration is much greater than the substrate concentration at half the maximum velocity. Now in that case, really the Km becomes negligible relative to S, and so at very high substrate concentrations, the initial velocity of the reaction is it doesn't matter what S is, to be honest. As S varies, it doesn't have much impact on the velocity. We've hit that plateau really there because the substrate concentration is so much higher than half Vmax. We've moved out of the linear part of the graph, we're in the plateau. So if you move the substrate concentration around in the plateau, it has no effect on Vmax, and so you pretty much, you're not going to change the velocity of the reaction if you're way above the Km. So in this case, the only way we can get Vmax to go up is we add more enzyme, and that then will go up proportionate to the rate at which we can convert the substrate to the product. So that's because you can't provide another substrate molecule any faster in this case. It's at saturating conditions, and so the substrates have been converted to the products. The only way you can get more product formed is to add more enzyme under these conditions. So that's the only way you can increase the velocity of the reaction there. The last useful thing we can look at is when the substrate concentration in the reaction is equal to the substrate concentration at half Vmax, so that's Km. So S equals substrate concentration equals Km at this point. And so there at that point, Km effectively becomes the substrate concentration plus the substrate concentration, which is 2S. The S's cancel out to give us Vmax over 2, and that really is the functional definition of Km, really, Vmax over 2, half the maximal velocity. So that just really gives us a mathematical confirmation of what Km is, of what half Vmax is. So that's kind of all that's really kind of useful at this point is the mathematical demonstration that when this substrate concentration equals Km, that Vmax is over 2. So last thing to look at here is this rate at which enzymes can actually do the catalytic event, and that's called turnover number, and it's called kcat. And so that again is the rate at which substrate is converted to product by a single enzyme at its maximal velocity. So what you see from the table here is that there's some enzymes over here on the left, and there's some substrates here. Don't worry about the Km for a moment, we'll come back. And then you've got the kcat over here. So this is given as a reciprocal of time, so it's per second or per minute, usually given as per second. So what you see here, there's some significant differences here in how quickly these things work. So carbonic anhydrase here, this second row down, that enzyme has a maximum turnover rate, a kcat, of 1 × 10⁶ per second. So that means 1 × 10⁶ substrates are being converted to product per second. That is an amazing turnover number. A few more A's here, not too fantastic. 8 × 10⁻², that's still pretty good, but it's faster than you and I could do anything per second. But not as fantastic as carbonic anhydrase. But the important thing here is that you see there is a range of turnover numbers. Some enzymes are very rapid, some are not as quick. So what does this mean? Let's look at the relationship between Km here and kcat. So is what you see is if you look at these relationships here, if one is high, the other is low. So here we've got 1 × 10⁶ and 1 × 10⁻². So the interpretation of that is, what that means is that if you have a high Km, so a high Km like this one here, you tend to see very fast turnovers. Okay, when you drop the Km down, you see slower turnovers. What this means, if you have a high Km, the enzyme has a low affinity for the substrate. The enzyme is unable to bind the substrate efficiently, so you need a lot of enzyme to reach the Km. If you have a low Km, you have a high affinity of the substrate for the enzyme. The enzyme binds the substrate well, it gets hold of it really efficiently, grabs it quickly, converts it to product, so you don't need so much substrate to get to that half Vmax. Low Km enzymes tend to have a high kcat. Okay, so there's a lot of math in there. Take it slowly, read each of your sections through, and it'll build up to the point where you can see the relationship between Km and kcat. Okay, that's it for the mathematics of enzyme kinetics. Don't forget the big picture. The point is to understand how processes in cells are really dictated by how quickly or slowly biochemical reactions occur, and really that's kind of what we can reduce cell biology down to at the end of the day is the processes which are regulated by structural elements, which we'll come back to and talk about in future videos, or we can think about the speeds and the kinetics of certain processes. So what we'll finish up with in this section in a little bit is taking a look at enzyme regulation. I'll see you soon.